Okay, good day and welcome to Dr. Hugh Ross's Paradoxes Sunday School class. Today is September 4th, 2022. Dr. Ross will be speaking on miraculous galaxies. He will be away next week, and Hugh Ross, one of our apologists, will be speaking. Ross Hoagland, excuse me. Get those Rosses mixed up. Sorry about that. Anyway, Ross Hoagland will be speaking on love and human psychology, a call back to Eden. Dr. Ross, please come up.
Testing. Oh, good. We're good to go. Thank you. Well, I've been told there's an excellent chance that we'll be able to move back to Pritchard Hall next Sunday. So I'll keep you informed of my social media sites as to whether that's going to work. And the church has asked if we could move back to a 12:30 p.m. start time. But again, we'll give you details. If that doesn't work out, we'll be meeting here next Sunday at 1:30 p.m. Pacific time. Well, this is part 2 of a series, Our Miraculous Galaxy. And last week, we talked about what would happen if you saw 16 consecutive rolls of the dice, and each time it came up snake eyes. The chance of that happening, if the dice are fair, is only one chance in a 6,000,000,000. And so even if you were to see 6 consecutive rolls of the dice, where it always came up snake eyes, you would draw the conclusion these dice have been designed to only produce snake eyes. We're talking 16 here, no doubt. When we talk about our galaxy, we're not just looking at 16 different features that are fine-tuned, uniquely fine-tuned to make life possible in our galaxy, in particular advanced life. We're talking over 100 features. And what I'm doing in this short series about our galaxy is just selecting some of the more significant of those 100+ fine-tuned features of our Milky Way galaxy that makes possible the existence of life. If you missed last week's class, we do archive them all at paradoxes.org, so you can watch or listen to the recording of last week's class, or you can download it and listen to it and watch it at your leisure. But we ended off last week by pointing out that our Milky Way galaxy, one of 2 trillion galaxies in the universe, but of all the galaxies we can observe in any kind of detail, we see that our Milky Way galaxy alone has the features of being the right size, being a spiral structure, being a barred spiral, and having the just right spacing between the spiral arms, the symmetry of the spiral arms, and a lack of very many feathers or spurs between the spiral arms. And we looked at the 15 galaxies that come the closest to matching our Milky Way galaxy, and it was UGC 6093 that comes the closest. And here you can see a side-by-side view of the 2 galaxies. You right away notice that the color of UGC 6093 is different from the Milky Way galaxy. Unlike the Milky Way galaxy, it does not have symmetrical spiral arms. The spiral arms are spaced roughly the same distance apart as they are in the Milky Way, but you do notice that the spiral arms are significantly distorted, particularly the ones that are close to where you could possibly have an advanced life site, namely about halfway out from the center of the galaxy. This is actually the region where you see the greatest distortion. Now, I put these 2 galaxies side by side, but they're not to scale. The Milky Way galaxy has a spiral armed disk that measures about 100,000 light years across, whereas in the case of UGC 6093, the diameter of its spiral disk is 220,000 light years across. So this is a much bigger galaxy than our Milky Way galaxy. And if you look at the core, you notice that you have a much brighter core in UGC 6093 than is the case with our Milky Way galaxy. And that's to be expected because a supermassive black hole in UGC 6093 weighs in at 26 million times the mass of our star, the Sun. You say, how about our Milky Way galaxy? Its supermassive black hole comes in at 4 times. So the supermassive black hole in UGC 6093 is more than six times as massive as the one in the Milky Way. But the biggest difference, the supermassive black hole in our Milky Way galaxy is in a very quiet phase right now. It's really not feeding on too much mass. I mean, what makes these supermassive black holes very bright, they're black, so no light comes out of the black hole, but just beyond what's called the event horizon. The event horizon is the distance from the black hole where nothing can escape, not even light itself. But matter that's falling in towards the event horizon gets converted into pure energy with anywhere from 6 to 42% efficiency. And you notice right away that the very center of UGC 6093 is a whole lot brighter than the center of our Milky Way, and that's because it is currently pulling in huge amounts of matter into its supermassive black hole. And so it's considered to be an AGN galaxy, which stands for galaxies that have an active galactic nucleus. An active galactic nucleus galaxy is a galaxy that's sucking in huge quantities of mass towards a supermassive black hole, and therefore is radiating extreme and deadly radiation from just beyond the event horizon. The other distinguishing feature is that UGC 6093 is classified as a mega maser. You may have heard of lasers. A maser is just like a laser, except that it's pumping out its radiation at microwave wavelengths rather than optical wavelengths. And this is a mega maser, which means that it's a very powerful maser, so powerful that the radiation coming out of it would be deadly to even primitive life throughout the entirety of the galaxy. So this is the closest galaxy beyond our Milky Way galaxy that has the features that matches our Milky Way galaxy. But as you can see here, it's so different from our Milky Way galaxy in all the ways that would permit life to exist. We've yet to find a galaxy beyond our Milky Way galaxy that could conceivably be a candidate for advanced life. We had some where astronomers speculate they might be candidates to host a planet orbiting a star on which you've got microbes. But even that is speculation. We don't have any galaxy that we know for sure where that could happen. Well, I'm going to spend the rest of my time giving some additional features of our Milky Way galaxy that demonstrate that it alone, of all the galaxies we can see in the universe, has the features that are required for advanced life, and how these different features are highly fine-tuned. And just like with a dice that comes of snake eyes, 16, 22, 32 times in a row, likewise we're seeing hundreds of features of the Milky Way galaxy where each shows a level of fine-tuning akin to getting multiple rows of dice coming up snake eyes, indicating this has been fixed, it's been designed, purposely designed to make possible the existence of advanced life within it. Okay, I'm going to proceed to another feature of our Milky Way galaxy that's highly fine-tuned to make possible advanced life, and that refers to the pitch angle. Now, the pitch angle is basically the angle between the tangent of a circle, which is the straight line you see to the left, and the tangent to the spiral arm. And in the case of our Milky Way galaxy, the pitch angle is 13 degrees. And if you were to change that by as little as a degree, you eliminate the possibility that our Milky Way galaxy could sustain advanced life. The smaller the pitch angle, the more tightly wound are the spiral arms. And so if you make the pitch angle any smaller, then the arms will be too close together, which means that any planet conceivably hosting life is going to be exposed to the gravity from the supergiant stars in the spiral arms, and also for the radiation coming out from the younger giant stars in those spiral arms. You say, what's the problem if you make the spiral arm, the pitch angle bigger? That means the spiral arms will be farther apart from one another, which means there's not going to be sufficient heavy element generation to make possible advanced life. A bigger pitch angle could make possible microbial life, but not advanced life like we see in our Milky Way galaxy. And so, just picking up on where we left last week, kind of like seeing 16 or more throws of dice always coming as snake eyes, we're seeing in each case the Milky Way galaxy has these extraordinarily fine-tuned features, and we recognize we're living in an extremely improbable galaxy. You know, one of the books I've written was titled Improbable Planet, a title that was actually suggested for my new book, Design to the Core, was Improbable Galaxy. Now, I just want you to kind of look at it. Clearly you see the extreme symmetry to the spiral arms, but we also notice that there's a color. Most galaxies are classified as blue galaxies or yellow galaxies. Our Milky Way galaxy is called a green galaxy. Now, it doesn't look green, but what you notice is in this image, you've got places in the galaxy where you got blue stars, other places where you got yellow stars. And it's about 50-50 of the blue and the yellow stars. And the blue stars are young stars, late generation stars. Our star, the sun, is classified as a third generation star, but it is 4.5 billion years old. And so when stars are young, they radiate in the blue part of the spectrum. As they age, they go to the white part of the spectrum. And our star, the sun, is now in the yellow-orange part, which is what happens when stars are several billion years old. And then stars that are really old, they're a deep yellow to an orange color. And what you see in the next slide is a side-by-side comparison of a blue galaxy with a yellow galaxy. And most of the galaxies we see in the universe fall into one of these two categories. The galaxy in the left, NGC 1309, is dominated by newborn galaxies. And yeah, you do see a few of the yellow stars, but notice there's not very many of them. And the ones you do see happen to all be in the core of the galaxy, and the core is tiny. It's not as big a core as you see in our Milky Way galaxy. This galaxy is heavily dominated by these young, large stars. And when stars are young, they're very unstable. They radiate, our star, the sun, for example, during its first 500 million years, was pouring out 10,000 times plus as much deadly radiation as it is today. Particles, gamma ray, and X-ray radiation. And so NGC 1309 is a galaxy that's dominated by these young, unstable galaxies pouring out deadly radiation. And what you see on the right is a yellow galaxy. And in both cases, I chose spiral galaxies. Only a few % of the galaxies in the present universe are spiral galaxies. The vast majority of galaxies are spheroidal or ellipsoidal galaxies or a regular galaxy. And these spherical and spheroidal galaxies, they make up about 90% of all the galaxies in the present universe. And they typically form as a result of irregular galaxies and spiral galaxies merging together. And when they merge, the spiral arm structure collapses, and you get this ball of tightly packed stars and gas clouds. But in this case, I chose to look just at galaxies that are spiral, like our Milky Way galaxy, but you notice they fall into two categories, the blue ones and the yellow ones. And you say, well, what about the yellow ones? these are old stars. And in NGC 3190, you're basically looking at a galaxy where most of the stars are older than our star, the sun. And I've often joked with audiences that stars are like human beings. They're unstable when they're young, they're unstable when they're old, they're maximally stable when they're middle-aged. But in the case of stars, the stability period is quite narrow. Stars either, they're unstable for more than 90% of their history. And so as stars age, they once again begin generating a lot of deadly radiation, and their luminosity is no longer stable. Our star, the sun, is the stablest star in terms of its luminosity of any star that's ever been observed. Astronomers have been searching for 65 years to find a star in our galaxy or in the Andromeda galaxy where the luminosity stability is as good as what we see in the sun. And the sun is 5 times better in its luminosity stability than the second best stable star that astronomers have been able to find. And the reason why is that once you get to stars that are even as slightly older than our star, the sun, or slightly younger, they become much more unstable. So in both these cases, blue galaxies or yellow galaxies, advanced life is not possible. You need to be in a galaxy like our own, where you got a mix of blue stars and a mix of yellow stars, where these young and old stars are distributed in such a way that none of them pose a risk to advanced life on our planet Earth that's orbiting our star, the sun. And one of the unique features of our star is it happens to be orbiting around the center of the Milky Way galaxy, where it's not exposed to the big blue stars, and neither is it exposed to those yellow stars we see in the center of the galaxy. We're about halfway out from the center of the galaxy. I'll show you in a minute exactly where we are. In fact, it's in the next slide here. We are in the inside edge of what's called the local arm. And we see that there are 2 significant spiral arms on either side of our local arm, the Sagittarius arm and the Perseus arm. The Perseus arm is one of the dominant arms in the Milky Way galaxy. But we're on the local arm, which is basically a splinter arm that breaks off from the Perseus arm. So if you see where our sun is and go to the right along the local arm, you can see where it joins the Perseus arm. And so our local arm is really a subarm. It's not a true spiral arm. It's a spur that breaks off from the Perseus arm. And our sun happens to be located on the inside part of the local arm. And we're going to zoom in on it a little bit, but what you're going to notice is our location in the local arm puts us 1,500 light years from the nearest gas cloud where new stars are forming, where we could be at risk for being exposed to deadly radiation. 1,500 light years is enough distance that we're well protected. But if you look along the local arm, you see that there really aren't any other locations where you get that degree of protection. And if you look closely on that local arm, in fact, let me zoom in here a little bit. Well, before we go there, I want you to notice how much smaller the Sagittarius arm is than the Perseus arm, and how many fewer dense gas clouds there are where new stars are forming, which could pose a radiation risk for the location of our sun. And if you look carefully at this diagram and you look towards the Sagittarius arm, towards the center of the galaxy, you notice that there's a gap in the Sagittarius arm where there are no maternity wards, no big gas clouds where new stars are forming, and no supergiant stars. So we're actually in a location on the local arm where we're in the best possible position relative to the Sagittarius arm. And notice we're closer to the Sagittarius arm than we are the Perseus arm. The Perseus arm is the one that poses a greater risk, and we're a little closer to Sagittarius and Perseus. But if you look outward towards the Perseus arm, you also notice, just like you got a gap in the vicinity of the sun and the Sagittarius arm, where there's no supergiant stars and no giant molecular clouds where you got these new stars forming, you see the same thing in the Perseus arm. As you look outward towards the Perseus arm, notice we're located to where there's a gap. Now, you're looking at a two-dimensional image here, because people always point out to me, well, I do see some of these pink spots that seem to be relatively close to us in the Perseus arm, and I even see a pink spot that looks really close to us in the local arm. Keep in mind you're seeing this in 2 dimensions only. That little pink spot, which actually represents the Orion Nebula, if you look in the 3rd dimension of depth, we see that it's really quite far away from us, literally 1,500 light years away. Same thing's true of those big pink spots you see in the Perseus arm that appear to be somewhat close to us. If you look at it in 3 dimensions, you see that they're actually quite far away. Well, this next slide, we zoom in a little bit more. And with a zoom in, you can see that indeed we're very well positioned in terms of being the best spot on the local arm relative to the safest place in the Sagittarius arm and the safest place in the Perseus arm. And then we zoom in a little bit, because that little circle you see there, that's actually about the size of what's called the local bubble. So we live in the local arm, but we live in what's called the local bubble of the local arm. The local bubble is basically a spherical region in the local arm that is underdense. So we live in an underdense bubble or region of the local arm. And by underdense, it's a place where there's not a lot of gas or dust and there aren't massive stars. It's really the safest place for our sun to reside, because it's a place where you're not going to run into molecular clouds that could gravitationally disturb the planets orbiting the sun, and likewise we're not going to be exposed to radiation from giant and supergiant stars, because we're in this underdense region. Now inside that underdense region, there's a region called the local fluff, and I described this in some detail in Design to the Core. So yeah, if you look at the chapter that talks about our Milky Way galaxy, there's actually a section there on the local bubble. And you say, what is the local fluff? Well, it's kind of like the word describes. It's a fluffy gas cloud of light molecules and dust, and all that works to protect us from radiation. The fluff that locally surrounds us in the local bubble absorbs radiation, so the radiation doesn't impinge on the surface of the Earth. And we have just the right fluff, just the right size and position. In fact, I have a map in Design to the Core where I actually show you where our sun is relative to the local fluff and the local bubble. And the whole point I'm making here is no matter how you look at our Milky Way galaxy, on the largest size scales, as we zoom into where we are in our solar system, we see features that must be extraordinarily fine-tuned to make the possible advanced life at this particular time on our planet Earth. All right, another feature. We need lots of heavy metals. For example, there's several heavy metals that are in your body. The human body, in order to thrive, must have a just right level of 22 of the 92 elements in the periodic table. And several of those elements are significantly heavier than iron. And so we need to be enriched with a lot of these heavy metals. And thorium and uranium, for example, are not vital elements. You don't want a lot of uranium and thorium in your body. They don't contribute to your biology. They're radioactive, but our planet must be super endowed with uranium and thorium, because they provide the long-lasting heat from radioactive decay that's necessary to sustain the Earth's magnetic field and the Earth's strong platonic activity. So this means that our solar system must form in a region of our Milky Way galaxy where there's a very high abundance of these heavy elements, but not remain there. Because the region of our Milky Way galaxy where you have the highest abundance of these metals is about 4 kiloparsecs out from the center of the galaxy. Where we reside right now is about 8 kiloparsecs out. And what you notice is that astronomers have now determined that to explain the abundance of the 92 elements we see in the periodic table, the solar system must have formed in that part of the Milky Way galaxy where the abundance of these heavy elements is at a maximum. But if we had stayed there, we would be exposed to the stars that generated these heavy elements. And now those are stars that pour out deadly radiation. It's also a place in our Milky Way galaxy where the density of giant stars is very high, which means those giant stars would be disturbing the orbits of planets around our star, the sun. So we can't stay there. But because there's a very high density of these supergiant stars, what happened was our emerging solar system, our star, the sun, with its newborn system of planets, it wound up having a gravitational encounter with several astronomers estimate at least 4 supergiant stars. And just like we send satellites to the distant planets using a gravitational slingshot, I mean, that's a standard feature when NASA wants to send a space probe to Jupiter, Neptune, Uranus, Pluto. They pick a time to send the spacecraft out where they can get a gravitational slingshot effect from Venus and Mars, as well as the Earth and the Moon, to send it out. And this is what happened to our emerging solar system. It had a gravitational encounter with several supergiant stars, which gave it a slingshot effect where it was catapulted away from the region where it got enriched with these heavy elements, but got catapulted outward and wound up landing in a place in the Milky Way galaxy where the abundance of these heavy metals is actually at a minimum. And that minimum is also a place where you're going to have the least density of stars, the least density of giant molecular clouds. This is actually one of the safer places in our Milky Way galaxy for advanced life. And you say, well, what stopped us? Because the catapult that the solar system experienced when it got ejected by a gravitational encounter with supergiant stars when it was 4 kiloparsecs away from the center of the galaxy, that would have kept us going, and it would have literally ejected us from the Milky Way galaxy. What happened was that our solar system experienced another encounter with supergiant stars, probably just before we got to our final resting place, which put the brakes on the solar system, stopped its outward catapult, and caused it to stop and rest, but stop and rest at the optimal place for advanced life. And so let me show you this on this slide where we can see where the sun was born in a region of our Milky Way galaxy where the star and giant molecular cloud density was extremely high, and where it also had an opportunity to encounter merging neutron stars, which would have super enriched the solar system with elements heavier than iron. Half the elements that are heavier than iron are made by the merging of neutron stars to become black holes. So it's crucial to get the abundance of heavy elements that the new forming solar system have a close encounter with a neutron star merging event, and also have a close encounter, not too close, but close enough, with several different kinds of supernova eruption events, and then get ejected after it's been appropriately enriched and sent out to where it is now. And you can see where the sun is now. We're in between the Perseus and Sagittarius spiral arms, but we're also on the inside edge of what astronomers define as the co-rotation distance from the center of our galaxy. Now, the stars in our galaxy obey Newton's law. And if you can remember your high school physics, Newton's law basically say that the farther you are away from the massive body that you're revolving around, the slower you'll revolve around that body. And we see this with the planets in our solar system. Mercury goes around the sun in about 90 days. That's because it's quite a bit closer to the sun. Venus takes more than 250 days. Earth takes 365 days. Mars takes about 2 of our years. And so as you move out from the center of our galaxy, we see that the planets take longer and longer to revolve around the sun. And that's exactly what Isaac Newton was able to establish from his laws of motion based on the law of gravity. Now, the stars in our Milky Way galaxy, they all obey Newton's laws. And so as you go to the outer edge of our Milky Way galaxy, these are stars that take over 1 billion years to make one revolution around the sun. Whereas where our star, the sun, is now, we make 4 revolutions every 1 billion years. And then stars that where the sun was, they'd be making about 7 revolutions around the sun for every 1 billion years, 7 or 8 revolutions. Now, although the stars obey Newton's laws, the spiral arm disk does not obey Newton's laws. Rather, it is driven by density wave physics. And so what's interesting is that the spiral arm pattern you see here basically operates like a rigid disk. So it's doing this, which means all parts of the disk are going around the center of the galaxy at the same rate. And so the disk structure is rigid, but that's not true of the stars that are orbiting around the center of the galaxy. And that little red annulus you see there, that's the distance from the center of the galaxy where the disk rotates at the same rate that stars would revolve around the center of the galaxy. Now, that's a safe region because with the stars moving around the center of the galaxy at the same rate as the spiral disk structure, that means those stars are going to be passing through spiral arms at the minimal rate. If they're exactly at the co-rotation distance, they don't move at all relative to the spiral arm structure. And you say, well, wouldn't we be better off if we were exactly on the co-rotation distance? Because that means we could be between 2 spiral arms permanently. But the problem with being exactly at the co-rotation distance is you get mean motion resonances. I'm not going into the details of that. I describe that in some detail in a book designed to the core. But what I point out is where you do get a mean motion resonance, this is where you get gravitational disturbances. So if we were exactly at the co-rotation distance, we would suffer one of these mean motion resonances, which would strongly eject our solar system away from the co-rotation distance. And what we notice is that our solar system is on the inside edge of the co-rotation distance. And being just inside the co-rotation distance, it does not experience these mean motion resonances. And so we don't experience any strong gravitational kicks. We're close enough in where that doesn't happen. It does mean that we do cross spiral arms, but we only cross spiral arms about once every 1 billion years. And the last time we crossed one was about 500 million years ago. So right now we human beings are existing on planet Earth at the optimal time relative to the movement of the sun around the center of the galaxy. And so this establishes what's called the galactic habitable zone. If you want to have advanced life, now there's been some speculation in the research literature that maybe you could have brief microbial life on a part of a planet orbiting a star that's a significant distance, say a few hundred light years away from the co-rotation distance. But now we're talking microbes that won't be existing for billions of years. They'd be existing for millions, at best tens of millions of years, and they wouldn't be globally distributed. And so if you want advanced life, a minimum requirement is that advanced life, plants and animals, must be preceded by 3 billion years of global, high population, very diverse microbes. You say, why? Because planets are born where they do have liquid water to make advanced life possible. The metals, the heavy metals, will start off being in soluble form. It's the microbes that transform the soluble metals that exist on an earthy planet into insoluble metals. And if we eat plants or food or whatever, we have to be careful not to consume a lot of soluble metals, because that means that we're going to be pushing these metals in our body up to a level that will be lethal for us. I mean, for example, too little iron in your body, you'll die. Too much iron in your body, you'll also die. The iron has to be at the just right level. And it was a huge quantity of sulfate-reducing bacteria that populated the Earth for 3 billion years that brought the soluble iron on planet Earth down to the just right level. So most of the iron we see in the surface of the Earth is in insoluble form. Incidentally, we get another benefit from that. We can mine those insoluble iron ores and use that to sustain our civilization. But it's crucial that we not have too much soluble iron in our environment, because that means we'll push the iron content in our bodies up to too high of a level. And hey, iron is just one of the 22 vital poisons, elements in the periodic table that must be at the just right level in soluble form. Incidentally, one of those is arsenic. Do you know you need arsenic in your diet to be alive? Too little arsenic, you'll die. But I'll tell you something, you only need a tiny amount of soluble arsenic in your diet to be at the level optimal for advanced life. If you push it up a little bit, and you don't have to push it up very far, you'll die. And so you all heard about that novel, Arsenic and Lace. I think that's the right title, where a woman poisons her husband by giving her her husband a little more soluble arsenic than he would otherwise get from eating plants. And so she murders him in that way. And you can do that with lots of other metals as well. I'm not recommending you pursue that, but just making the point that we really owe a huge debt to our planet being in the right place in our galaxy where our planet can sustain a huge abundance and a huge diversity of microbes to chemically transform the crust of the Earth so that plants and animals would be possible, and eventually human beings. Thanksgiving's coming up in a couple more months. I hope when you celebrate Thanksgiving dinner, you'll thank God for those billions of years of microbial activity that brought the soluble metals in your turkey down to the just right level, and the soluble metals in your vegetables that accompany your turkey down to the just right level. Hey, I've gone over my 30 minutes. I thought I was going to be able to do this series in 2 parts. We're going to do it in 3 parts. So next time I'm back here with you, we'll do part 3, but we'll be able to finish it in 3 parts. So, and incidentally, just for your benefit, I did put some content in here that's not actually in Design to the Core, and you'll see even more next time. Say, where did all this new content come from? Hey, my literature search for my book Design to the Core ended about 15 months ago. And there's been a whole lot of new stuff published in the scientific literature. So what I'm wanting to do is actually give you some bonus features here of design features we see in our galaxy that didn't make it into Design to the Core. And it's demonstrating a biblical principle. The more we learn about nature, the more evidence we accumulate for the supernatural handiwork of God. And I'm actually looking forward to bring out a 2nd edition of Design to the Core. Even though it's only been out for 2 months, there's already been a huge abundance of scientific papers that allow me to make an even more spectacular case for supernatural design. I'll stop there. We'll take questions. And as usual, we'll alternate between people that are here in person and people that are online. So do we have an online question we can start with? Not yet? You got a question
You
from
want to
the
do
floor?
an
then?
online? Jamie's going to be hosting this today. So.
Okay.
All right, so I have a question about Jupiter. This is Mark Durham, by the way. There's discussions going on now about Jupiter's protective nature for Earth by deflecting inward-bound asteroids away from the Earth. Some now believe that Jupiter sometimes deflects some asteroids towards Earth.
Correct.
And so it's not, is it not the protective giant we thought it was? Or?
Well, you want your, excuse me, you want your planetary system set up so that we get just the right delivery of asteroids and comets. So you don't want a situation where the gas giant planets provide such a strong gravitational shield that we don't get any comets or asteroids at all. So for example, our planet Earth loses a very tiny amount of water to interplanetary space every day. The tiny amount we lose, and it's only a tiny amount, gets replenished by comets that bombard the Earth. And we get bombarded by about 10,000 comets a day, most of them really tiny. And comets are 85% frozen water. So the tiny amount of water we lose is replenished by the tiny amount of water we get from comets. If Jupiter, Saturn, Uranus, and Neptune gave us perfect protection, we wouldn't have that delivery. And that wouldn't be a problem for a few million years, but it would be a problem if you want life on the planet for billions of years, which is what you need if you want to eventually have advanced life. And what you'll see in my book, Design to the Core, is that it's important that a few asteroids get through, because there are asteroids in the different asteroid belts of our solar system that are composed almost entirely of very valuable heavy metals. In fact, NASA has found an asteroid in the asteroid belt that they value at about $50 quadrillion because of its superabundance of platinum, gold, silver, uranium, thorium, palladium, metals that are extremely expensive on the market. And so it's important that the gas giants let some of this through. And one of the papers I cited in Design to the Core makes the point that the mass of the moon and the present orbit of the moon actually acts as a funnel to deflect the very dense heavy metal asteroids away from the moon and towards the Earth. So the moon actually acts as a delivery funnel to bring in a few of these asteroids that are super endowed with these heavy metals. I'll give you a couple of examples. 80% of the gold and platinum that's in circulation in our economy today comes from South Africa. It comes from a location outside of Johannesburg where tens of millions of years ago a big asteroid struck, and it penetrated the ground, and as it penetrated, it actually caused a volcanic eruption to take place, but that volcanic eruption brought up heavy metals from the mantle of the Earth, which complemented the heavy metals that were in the asteroid. And so that famous gold mine outside of Johannesburg, they're basically mining an asteroid that struck more than 100 million years ago, and also mining the material it brought up from the mantle as a result of that collision. And so we're all beneficiaries of that asteroid that struck in South Africa. Another example, you go to the north shore of Lake Huron, you'll see the city of Sudbury. It's a city in Ontario, Canada, of more than 100,000 people, and the city of Sudbury is sitting on top of an asteroid collision. Over half the nickel that's in circulation in the world today comes from that one asteroid that struck. So no, you don't want asteroids like that hitting the Earth every year. If that were to happen, it would eliminate the possibility of advanced life on the planet. You want a few of these asteroids to penetrate into the crust of the Earth, but only a few. You say, about how many? Well, you probably want them to hit at a rate of about every 100 to 200 million years. So you want them to be rare, and you don't want any to be hitting during the present era. I mean, a big asteroid striking the Earth today would wipe out all of humanity. So, yeah. And what's interesting about our solar system, and you'll see this in Design to the Core, in order to get the perfect shield, where you have some comets coming through and a few incidental asteroids coming through at just the right rate of just the right type, it's crucial that you have a gravitational shield where you got a giant planet that's the most massive and the densest, that is closest to the Earth. Jupiter, for example, has about 3/4 of all the mass of the solar system planets. But it's important, in order for the shield to work, that it be the closest of the gas giants. It's also important that the second best shielding gas giant be the next closest to the Earth, and that would be Saturn. And then for the shield to really be optimized, you want 2 more gas giant planets, both of which are significantly less massive than both Jupiter and Saturn. And that's what we have in our solar system. We got these 4 gas giants orbiting in such a way that they do not generate mean motion resonances, but they operate as a gravitational shield that lets in just the right amount of comets and asteroids. Long answer to the question. There's 2 chapters that give you a more detailed answer if you want it in Design to the Core.
That has nothing to do with kimberlite diamonds, asteroids, or is that strictly an Earth?
Okay, the kimberlite diamonds, which I also address in Design to the Core, is a feature that can be blamed on the internal structure of the liquid core of the Earth, the inner mantle, the outer mantle, and the plate tectonics, where you get carbon driven in to the mantle, but in such a way that it's driven deep, and then it comes up and forms these long tubes of hyperdense carbon, and hyperdense carbon in the right form produces diamonds. Okay, internet question.
Okay, we got a question from the internet. Doug McComb from Southern California. and this, it's a bit long here. So he says, I think it has been revealed that light consists of particles, photons, and can be affected by gravity, etc. But what does heat consist of? Does it consist also of particles? Does heat consist of particles, and does heat have, quote, zero rest mass?
Okay, good question from Doug. And Doug, if you're watching this, looks like next week we might be actually back in Pritchard Hall, and that's close enough that you can join us in person. So look forward to that. But heat and light are one of the same. They're both part of the electromagnetic radiation that permeates our universe. And so heat is typically light at infrared wavelengths. And so if you ever had one of these heaters you put in your home, you notice it radiates with a red glow. Well, actually, most of the radiation coming out is at infrared, where our eyes can't see it, but we do feel the heat. And so electromagnetic radiation at infrared wavelengths, we feel that as heat. It's made up of photons, and yeah, Doug is right. Photons can be influenced by gravity, but they need a lot of gravity to experience an influence. So you need a huge, massive, dense body so that photons passing by the body are gravitationally bent. So for example, light that passes by our star, the sun, it gets bent by the gravity of the sun. So our sun can actually act as a lens. And I think a few weeks ago I actually showed you a James Webb Space Telescope image where you could see a galaxy cluster operating as a gigantic gravitational lens, bending the pathway of photons that go by it, and bending it in such a way that galaxy cluster actually operates like a telescope. In fact, astronomers take advantage of gravitational lenses, both stars and galaxy clusters, where they get a magnification effect of up to 8,000 times. And so explains why we're able to see distant galaxies. If you can take advantage of a galaxy cluster between you and a distant galaxy, you can actually get a factor of 8,000 times magnification. And so this is a great assist to our telescopes. And so astronomers are eagerly taking advantage of these gravitational lenses. In fact, a friend of mine at Caltech, his research endeavor is to look at individual stars that are between us and another star where the star has planets. And if you get them perfectly lined up, the gravitational lens of the star between us and the distant star can be powerful enough so you can actually image the planets that are orbiting that more distant star. Gravitational lenses are amazing. Huge boost to astronomical research and a direct outcome of Einstein's theory of relativity, general relativity. Okay, Norm.
Yeah, hi. Back to your introduction, where you described, and you've talked about this before, where you've described how as matter approaches the edge of the black hole, and as matter gets transported through that edge into the black hole, we have this radiation. The mass is accelerated and gives off radiation of mass equivalent to, or energy equivalent to a large percentage of the mass. Can you explain the mechanism for that, so that some of us can understand that? What is the mechanism for the transformation of that mass?
Yeah, very
into
good
energy?
question. And so these supermassive black holes are rapidly rotating, and the faster the rotation, the greater the convergence. And what's happening is these particles or planets or stars or asteroids are being sucked in towards the event horizon. Because of the rotation of the supermassive black hole, they wound up spiraling around the supermassive black hole. And so as that matter comes towards the event horizon, they spiral in and the orbit gets smaller and smaller, and it gets sped up by the gravity of the supermassive black hole. So it reaches a point that just before it enters into the event horizon, those particles or bits and pieces of matter are moving at just under the velocity of light. And then, they're being accelerated. So you got this acceleration as well as this very high velocity. And that explains why you get such an extremely efficient conversion of matter into energy. As I explained in Design to the Core, if the rotation rate around the black hole is relatively small because the black hole isn't rotating very fast, you get maybe 6% of the mass being converted into energy. But where the supermassive black hole is rotating rapidly, which causes these massive bodies to spiral in at a very high velocity, the conversion rate can get as high as 42%, which is the highest conversion rate of matter and energy we see anywhere in the universe.
So what you're saying, basically, by accelerating the mass to near Earth, the speed of light, permits that conversion of the mass into electronic energy.
That's correct. And then you also get an acceleration effect because of the fact that it's, you got an orbit that's getting smaller and smaller. And so, yeah, that's where you get this big transfer of energy. And there is a brief description in Design to the Core. I don't give you a complete analysis. Basically, I cite papers that do that for you. And they're really accessible, and the papers can be read for free.
Tell me if you already answered this, and I have a question after this one of my own. So, Craig McMahon asks, how can the efficiency of mass to energy be so efficient near supermassive black holes? How can it be so high given the much lower efficiency of thermonuclear explosions?
Yeah, I think I just explained that. That was Norm's question, as to how you get that extremely high conversion of matter into energy. And there's about a 3-paragraph description of that for people who don't remember what I said to Norm in Design to the Core.
Okay.
And by the way, there's some really good videos you can watch online. Go to YouTube. I mean, YouTube's got almost everything, right? If you need to do surgery on somebody, it can show you how to do it. Not that I recommend you do that. If you need to fix something in your car, you can watch a little thing, but you can also watch a little video clip of what happens when different particles or bits and pieces of matter get close to a black hole, and how you just see it spiraling inward like this, and eventually it gets sucked into the event horizon.
I agree. YouTube is very helpful. I fixed my couch this week, my recliner, by using YouTube.
Yeah, you can fix anything by watching a YouTube video clip. It even tells me how to tie a tie. I had to tie a tie for a TV show and having trouble, so I just got a little video clip from YouTube.
So I was perusing and I saw some headlines this week. I didn't have time to delve into the articles I read that I saw, but there's some talk online about the James Webb Telescope revealing that the Big Bang may not be so. What arguments have you heard? What's on the...
Yeah, I'm all over that, Jamie. And I've already posted a couple of short paragraphs on my social media, but on September 12th, I got a 2,500-word article that responds in detail. And this is coming from a plasma physicist, Eric Lerner. He's well known for writing the book, The Big Bang Didn't Happen. I've debated Eric Lerner on the radio. And in my debate, and by the way, I respond to him in some detail in the 4th edition of The Crater and the Cosmos. And he's a fan of Hans Zelvane. He's a Nobel laureate in physics. He passed away several decades ago. But back in the 40s and 50s, he was promoting this idea that the way to understand the universe is to recognize that the electromagnetic effects dominate the gravitational effects. Now, this is before astronomers had the capacity to measure the magnetic fields of galaxies and the intergalactic magnetic fields. What I pointed out in the debate I had with Eric Lerner, and also on The Crater and the Cosmos, is that we now have reliable, accurate measurements of the strengths of magnetic fields in galaxies of all different types, as well as the strength of the intergalactic magnetic field. And these fields are below a nanogauss in strength. So less than a billionth the magnetic field of the magnetic field that is surrounding our planet Earth. And basically making the point, with magnetic fields that weak on large scales, gravity dominates the dynamics of the universe, not electromagnetic radiation. But if you read Eric Lerner's book, he's very opposed to Big Bang cosmology for theological reasons. He's an atheist, and he realizes that if he concedes it's Big Bang, that means there has to be a Big Banger. That implies the universe has a beginning, and there needs to be some causal agent that actually starts or begins the universe. And then you got the space-time theorems. And so he's arguing that the way to bypass the implications of the space-time theorems of general relativity is to say that general relativity is not the dominant factor in governing the dynamics of the universe. But it really is. The evidence is overwhelming. And I'm a little bit disappointed in Eric Lerner that he's not conceding that fact. But if you go online, you'll notice that dozens of astronomers have jumped all over him for making the claim that the latest images from the James Webb Space Telescope disprove the Big Bang. They do the opposite. They provide more evidence for the Big Bang than we had before the James Webb Space Telescope. It's the opposite of what Eric Lerner is claiming. Now, what I've done in my article, and I've already done this in one post on my social media, it's on my Facebook page, is to say this is deja vu. If we go back to the 1960s, that's when they discovered quasars for the first time. But there was also an alarm that went out because the first quasar they found was 3C273. And for the Big Bang model would predict that quasars like 3C273, which is it's the brightest quasar in the sky and relatively close to us. And basically, the Big Bang model tells us quasars like that should be quite rare. And that was the first quasar we found. So people were presuming, hey, these quasars are common, they're not rare. But what they're overlooking was the closest and brightest quasars obviously are going to be the first that we're going to find. It doesn't mean that they're automatically the rarest. Here we are 65 years later, and guess what? 3C273 indeed is very rare. And we only have a handful of quasars that are closer to us than 3C273. And 3C273 still ranks by far as the brightest quasar in the sky. And so when we're seeing the same thing today, the James Webb Space Telescope is telling us we seem to have an overpopulation of spiral galaxies that are fully formed in the early universe. But guess what? Those are going to be the galaxies that will be the easiest to detect. And the James Webb Space Telescope has yet to take an image of the early universe at the deepest level it's capable of. So yeah, the initial images are showing us the easy to detect ones. It's not a complete sample. So I'm on record as saying when we got a complete sample, everything's going to fit what the Big Bang predicts. And by the way, there are a small number of Big Bang creation models that actually predict that the early universe will have a large number of well-formed spiral galaxies. So it's not what Eric Lerner claims, where he says none of the Big Bang models predict this. Many of them do. And it's something I've actually written about already, is we're already seeing firstborn stars. I've written 3 articles on that in my Today's New Reason to Believe, basically saying we don't have to wait for the James Webb Space Telescope. We're already seeing firstborn stars. But the firstborn stars we're seeing are the ones that are Milky Way galaxy. And they're the small firstborn stars. And by being small, they can burn for billions of years, which is why we're able to see them now. The big firstborn stars burn up very quickly. The only way you're going to see them is by looking more than 13 billion light years away, which means those stars, being so distant, are going to be very difficult to detect because they're not going to be bright enough, even with the James Webb Space Telescope. The James Webb is going to have to be fortunate enough to find a cluster of these firstborn high-mass stars. Now, because these high-mass firstborn stars burn up quickly, their ashes wind up polluting the small firstborn stars before those firstborn stars form. The really high-mass firstborn stars form in just a few tens of thousands of years, and they complete their nuclear burning in less than 1 million years. Whereas the small firstborn stars take 1 billion years to actually form. And during that 1 billion years, they get polluted by the ashes of the really high mass firstborn stars. But I've written articles making the point. These small stars that we see, yes, we can see the pollution, but the pollution is something that only matches them being polluted by the ashes of the really big firstborn stars, which is why astronomers concluded they too are firstborn stars, but they form so slowly they wind up getting polluted by their bigger brothers before they actually ignite nuclear fusion. Now, if you have lots of these firstborn stars that are high mass, that would predict you're going to have fully formed spiral galaxies, lots of them in the early universe. And one example is our Milky Way galaxy. We have measurements that tell us our Milky Way galaxy had a fully formed spiral structure more than 13 billion years ago. So it's a known example. Long before James Webb Space Telescope went up, we already knew that our Milky Way galaxy was in that category. Now, what James Webb's going to do for us is tell us what is the true abundance level of these fully formed early spiral galaxies relative to all the other galaxy types in the universe. Where Eric Lerner was misrepresenting the sciences, these first images are not able to give us the true abundance ratios of these galaxies. That will be forthcoming.
How are we doing on time?
One more question, then we'll end it.
Well, I got like 3 more questions. So
Okay,
let me
well, we'll
see.
take 1 or 2.
I guess we'll do, I suppose, okay, Mr. C. Depew asks for his brother Isaac from Indiana. Where do negative emotions come from? Are negative emotions a consequence of sin, or could they exist before the fall of Adam?
I think he means negative emotions, not negative motions. Am I right?
Emotions, yeah.
Emotions, okay.
That's my Midwestern drawl.
Right. Well, it's like people saying, hey, if you're really a follower of Jesus Christ, you got no reason to be depressed. And so Christians shouldn't be depressed. On the other hand, there's lots of physical abnormalities that can happen within your body, your gut bacteria, and in the brain that will cause you to be depressed even when everything around you is encouraging you to be filled with overflowing joy. And so there may be medical reasons why you're experiencing negative emotions. I mean, my son is a clinical neuropsychologist, and he's basically making the point if people aren't sleeping right, they're not getting the right diet, they can wind up having a chronic anxiety issue. And so people wonder, why am I anxious all the time? I have no reason to be anxious, but it's because of their lifestyle and also because of the way their body, particularly the interface between your gut microbiome and the brain, that could be out of whack. You might be having Parkinson's disease. There's all kinds of abnormalities that can generate that. You could have a brain injury. So, my son actually says, well, what kind of sports do you play? And says, well, if you just stop playing soccer, maybe this would go away. Or don't head the ball when you're playing soccer. So, and I would make that point before you go see a therapist and say, what's wrong with me? What am I doing that's spiritually problematic? You want to eliminate the physical causes for why you're experiencing these emotions. And if that's eliminated, then go see a trusted, experienced Christian therapist and say, okay, what am I doing in my life? What about my work? What about my relationships that's causing me to be feeling depressed and anxious when I shouldn't be feeling that way? So hopefully that addresses it. And by the way, I'm not a psychiatrist, so it's like I'm not really the person you should talk to. This is not my area of expertise. But I've had enough conversations with my son to kind of give you at least a start on how to deal with that.
Right. Do you think the negative emotions could have occurred before the fall of Adam?
Were there negative emotions before the fall of man? Well, as it says in John 16, in this world you'll have thermodynamics. Take heart, I've overcome the thermodynamics of the world. That's a paraphrase. It says tribulation. But the whole point is the very existence of the laws of physics, and the Bible tells us these laws have always been here. They've not been changed. That in itself is going to generate negative emotions. So, for example, if you're being attacked by a saber-toothed tiger, you'll probably feel fear. But that's a good thing. That's going to cause you to take the appropriate action to avoid being killed by this tiger that's looking for an easy meal. And so there are times when it's necessary to feel anxious, to feel fearful, to feel depressed. It's a way these negative emotions actually give you the necessary motivation to take the action to be delivered from these threats. Now, where it becomes a spiritual problem is where the threats don't exist. There are no threats, and this means, okay, you're probably not engaging God and your fellow human beings in a way that's appropriate, because there really is nothing in your environment that should be generating these negative emotions. And that's when, again, when I'd say you need to get some help from a skilled Christian therapist.
When you mentioned the diet, my wife looked over at me really funny. I'll just have you know.
Diet?
The diet.
Well, for the past 2 weeks, as a matter of fact, he's staying with us next week as well. We have a visiting scholar, and he's got a doctoral degree in nutrition. He's considered one of the top nutritionists in the world. And we've already done several video clips with him. He's writing papers. But he's making the point that diet has a huge impact on how you feel and your spiritual health. And so, and I've been glad that he's been here because we have several of our staff people that really do need to change their diet. And I've been telling them for years, you'll have a much better walk with the Lord with one another if you just change your diet. Maybe you want to avoid those donuts that are over there.
I was just going to mention the donuts.
So, and, you know, the number one advice I'd seen from Jim Painter is, he says, the problem with the American diet, over half the food you eat is processed. And he says, just eat whole foods. If you just eat whole foods, avoid the processed foods. But he showed me a diagram basically saying that the average American adult, 57% of the food they take in is processed. So just getting all those chemicals out of your body, eating whole foods, is going to make a big difference in your health and well-being. My son has written several papers on this, basically making the point, because he's done a lot of research on dementia and Alzheimer's, says certain foods that will really help you avoid that, even if you got a genetic proclivity towards that. And if you're interested, he says you want to eat dark berries that have a low sugar content. So like wild blueberries, especially wild boreal blueberries, they're not the tastiest blueberries, but they do give you the best brain health. Garlic is good, fresh garlic is good, ginger is good. So you can actually go online and read his paper about what foods you should eat. And bottom line is, he says, the number one food you should avoid is sugar. And you really want your brain to be feeding on ketones, not sugars. And Jim Painter last week gave a great lecture to our staff here, which got recorded, is going to go up on our YouTube channel, saying that Americans also the problem in that they're eating all day long. They get up and they have a breakfast, and they have 11sies, and then they have lunch, then they have all these snacks, they have dinner, and they actually eat just before they go to bed. And he says, if you actually structure it, and this is hard to do, I tried doing it and I couldn't do it, eat all your food in 8 hours. Says, eat all you want to eat, but consume all your food in the 8 or 9 hours. And what that does is during those 16 hours, your brain feeds on ketones for its energy rather than the sugars, and how much better the brain operates when you do that, and how your intestinal tract really flourishes well when you have these periods of fasting. And he says, all we're talking about is 14 to 16 hours. We're not talking about fasting for 40 days. Just do that. But frankly, I tried that and I was losing weight. I have a hard time keeping my weight up, trying to consume all my food in 8 hours, because I forget to eat. You get busy doing your work, so yeah, I should have been eating. But my son, he's on an 8-hour diet, and he says, for the first 3 weeks, he was losing weight, then he was able to stabilize his weight. He says the key is, eat your 3 meals a day, but eat them within an 8 to 9 hour window. So that's just kind of a quick précis on the lectures we've gotten from Jim Painter. He's written dozens of papers you can read. He's giving more lectures this week to our staff.
He's the visiting scholar.
He's a visiting scholar.
Jim Painter. Got it. Okay, do you have time for one more?
One more, and then
Real
we'll
quick
wrap it up.
one. Sorry we didn't get to everybody, but Justin asks, is there any evidence of Jesus' deity in the Old Testament?
Any evidence of Jesus' deity in the Old Testament? Yes, probably the best passage is one in the book of Jeremiah, where it talks about the name of the Messiah Redeemer. And the name he is given is the name Yahweh. He takes on the same name for deity that God the Father takes on. And so this is another one of many passages in the Bible that support from the Old Testament the doctrine of the Trinity. Father, Son, and Holy Spirit, all equal in power to one another. They're all part of that God that's one essence in 3 persons. None of them are inferior to one another, but they do divide their labor. They take on different roles with respect to humanity, roles that are described in 1 John, the New Testament epistle, where it says God is light, referring to the triune God, and how God the Father is the one that bestows love upon us human beings. God the Son bestows life, and God the Spirit bestows truth. Now, they're all involved in giving us truth, life, and love, but the Father takes a predominant role in bestowing love. The Son takes a predominant role in bestowing life, and the Spirit the predominant role in revealing truth. But yeah, the fact that you see in the Old Testament the second person of the Trinity taking the title Yahweh is definitely, I think, incontrovertible proof that he is fully God. And I think there's more evidence for that. The Jehovah's Witnesses, which visited me yesterday at my door, if you look at their Bible, they changed that passage in Jeremiah. And so the fact that they altered that passage means they know the significance of it. It really does establish that Jesus is God. Okay, next week we got Rose Hoagland teaching the class. I'll be back the next time I'm in town, which will be in a couple of weeks. Thank you.